Okay, today's lesson we're going to be describing N behaviors. One of our goals for today's lesson is to learn to use limit notation. So we're going to learn to use limit notation during this to describe N behaviors. We're also going to be looking at finding horizontal and slant asymptotes for rational functions. So we're going to mix a little bit of polynomial functions and a little bit of rational functions today, reviewing the information that we sort of saw last year and extending it a little bit with the use of limit notation. So from last year, polynomial N behavior. The N behavior of a function describes how the function behaves as it moves infinitely to the left or to the right. So we look at what the function is doing as the x values move infinitely to the left or infinitely to the right. So this is to the left because we're going in this direction. And this is to the right. The x values are going in this direction. And we're interested to know how the y values behave. So in order to describe the N behavior as we go to the left. So if we're going to the left, that means the x values are continuing in this direction. So the left N behavior is up here. So to pose the question mathematically of what it means to have to move infinitely to the left, this is the notation. And listen to how we read it. We say the limit of x, the limit as x approaches. Let me just do that again. So there we go. This means the limit as x. This arrow means approaches negative infinity of f of x, and then we can say what happens. So in words, that means as the x values decrease without bound, the y values of f of x do ... whatever. We can describe the N behavior as x increases without bound with this limit statement. The limit as x approaches infinity of f of x. And in this case, it means as the x values increase without bound, the y values of f of x do ... So in this statement here, we can see that as x increases without bound towards negative infinity, what do the y values do? Jude.
Increase without bound.
So as we approach negative infinity, so the limit as x approaches negative infinity of f of x approaches positive infinity. So what happens as the x values increase without bound towards positive infinity? What do the y values do? John Jean. What as the x values increase without bound towards positive infinity, what do the y values do? To where? So they decrease. But what we want to do is we want to use the word approach. So we would say that they approach negative infinity, or they decrease without bound. One of these two phrases would be the correct phrase. So the limit as x approaches positive infinity of f of x approaches negative infinity. And this is the way that we describe it. So have a go at practicing that now. Here's two sets of limit statements. Sketch a graph that meets these ones. You have 4 minutes for this. For both. So for this question, there's going to be multiple possible correct answers. But our first statement says the limit as we go towards negative infinity is going to go towards positive infinity. So our graph needs to exit up in this direction. That's described by this limit statement here. The second limit statement says as we approach positive infinity, the function will approach negative infinity. So it needs to exit off the graph in this direction. What we choose to do in between is up to our creativity. Make sure with this type of question, if you're getting a bit too creative like that, that you do at least create a function. It's got to pass the vertical line test. So none of this. It would be most sensible not to be so creative. This is math. It's not about creativity. Okay, so the next one, we're going to head off towards positive infinity in both directions. So something like this. Okay, so polynomial end behavior. For a polynomial equation, it's easiest to find the end behavior at the right side first. So if the right side, if you're looking at an expression, if the right side has a positive lead coefficient, then it's going to go up towards positive infinity. It's going to go up towards infinity. If the lead coefficient is negative, it's going to go down to negative infinity. So always start by sketching the right side first. Once you've sketched the right side, if the degree is even, it's going to go in the same direction. If the degree is odd, it's going to go in the opposite direction. So, in summary, it's going to infinity if the lead coefficient is positive. It's going to negative infinity if the lead coefficient is negative. If the degree is even, it's going in the same direction. If the degree is odd, it's going in the opposite direction. So I'm going to have a go at writing a limit statement for this polynomial expression given here. So firstly, what is the value of the lead coefficient? -3. So if the lead coefficient is negative, we can say that the limit as x approaches infinity of f of x is going to approach, well, it's going to go towards negative infinity because the lead coefficient is negative. Next up, we do the left-hand limit, which is the limit as x goes towards negative infinity of f of x. Now, what is the degree of this? Isn't it? 4, which means it's even. This means it's going to go in the same direction. This means it's going to go in the same direction. Have a go now at this one for yourself. 2 minutes for this one. Volunteer their limit statements. Let me have somebody fresh. I can take. Sorry, what was your name? Rudra. Okay, Rudra. Give it to me.
Why infinity is 1 infinity?
Sorry, I have no idea what you're talking about. Please use the correct mathematical vocabulary.
Oh, as the x value.
No. It's very precise. You have to have we start with the word the. The limit
As x approaches minus infinity.
as x approaches negative infinity.
Y approaches infinity.
No.
Or f of x.
What's the function here?
G of x. Sorry, g of x.
Of g of x.
Approaches infinity.
Nope. Let's start with the right-hand limit. What is the right-hand limit? Zane, help him out. The limit as x approaches infinity, positive infinity, of g of x approaches positive infinity. Why? Because the lead coefficient is positive. So the left-hand limit will approach will approach where?
Positive. Wait for negative.
Negative infinity. Why? Because the degree is odd. Because the degree is odd. You need the reasons as well.
If you were like saying this out like in words, how would you say the notation?
So there's two ways to say. I can read the mathematical notation that's given here, which would be the limit as x approaches negative infinity of g of x approaches negative infinity. Or I could say as x increases without bound, as x decreases without bound, g of x will decrease without bound. As x increases without bound, g of x will increase without bound. It's given, so the oral explanation of that one is given here. So as x values decrease without bound, the y values of f of x, and then you have to say will increase or decrease without bound. But if you're reading this notation, we're very precise. The limit as x approaches negative infinity of g of x approaches negative infinity. Sometimes it can equal a value. Typically, we would say when it approaches negative infinity, you can never equal negative infinity. So typically, in a more formal sense, the limit does not exist in these two. There is no limit. Usually, if we're looking for the limit value, it's usually equal to some value. But in these particular cases, in a more formal math course, you would say this does not exist when it goes to an infinity. All right, little review for rational functions. If you remember, a rational function is any function where you have the quotient of two polynomial functions. A rational function is any function where you have the quotient of two polynomial functions. Now, the end behaviors of this one is fairly easy to describe in the first two cases. So, in a case of a rational function, we would take the lead terms. Let me explain this. Let me explain this idea. So if you get a rational function, let's say f of x, it could be equal to 3x minus 2x to the power of 4 plus 1 all over 3 minus 2x squared plus 6x to the power of 5. Let's say we take this one. So as we're approaching positive infinity, we're putting large numbers in. What's the value of the numerator? If I take the numerator, rearrange it into standard form so we can see what the lead coefficient is. Imagine I put the value 0 in. If I put the value 0 in, g of 0 is going to equal 1. So the third term is very important there on that one. If I put a small number in, like g of 1, this is going to be minus 2 plus 3 plus 1. So all three of the coefficients really matter. Let me put in not even a big number. Let me put in a smallish number, like this one. So this is much bigger. Now, what am I going to get? I'm going to get minus 2 to the 10,000 to the 4. So this is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I'm going to get this number plus 3 times this number plus 1. Now, how important is that plus 1 in this number? It's not very important at all. In fact, sorry, can you take your earbuds out? How important is the 3x?
It would be.
It's insignificant. Let's say we were giving this number to 5 significant figures. That 3x and that 1 is not going to change the value to 5 significant figures whatsoever. Absolutely, it's insignificant. So for really large values, this function is approximately just this function. Because I'm only putting in 10,000. How much bigger than 10,000 is infinity? How many times bigger is infinity than 10,000? Infinitely. You get the sense that it's really, really big number. So it's almost equal to these values. When you get really large numbers, it's only going to be equal to these values. So as we go towards really large values, this basically just becomes this function.
Divided by 6x.
So for really large numbers, that number because the denominators are different, that really large number is much, much bigger. The rational function in the denominator is going to produce a much, much bigger number than the one in the numerator. That to the power of 5, the 6 has no effect in this case. The 6 and the -2, the coefficients, have no effect. For really large numbers, this doesn't matter. This doesn't matter. In fact, this is going to cancel out, and we're going to be left with this. So for a really large number, this is basically this function. For really large numbers, this simplifies down to that. So for a really large number, as we go towards positive infinity, what will be the value of this function?
Infinity, as we approach infinity.
How does this graph look? Think to last year. This is the polynomial. This is the rational parent function. We call it the reciprocal function. You should know off by heart how this graph looks. Carlos? No. How does this graph look? Really, for anything to do with rational functions, this is what we call the parent function for all rational functions, and it's very important to know how it basically looks. So it's going to look like this. So as we go towards positive infinity, what will this approach? 0. As we go to negative infinity, what will this function approach? 0. This is case 2. So this is case 2. So if we have this as our rational function, we have n in the numerator as the exponent and d as the exponent in the denominator. If n is less than d, as it was in this case, then the horizontal asymptote is y equals 0. Let's go back to that example and see what would happen if I change it up just a little bit. Let's change that number now to 4. So what rational function would this be approximately? Yes? Negative 2x to the 4 over 6x to the 4. If you simplify that algebraically now, discuss with the person next to you. Simplifying that algebraically, what number does it become? To the person next to you, quietly. Okay, let me have somebody fresh. Yusuf. Minus 1 over 2. So this is going to be minus a half. So what is the horizontal asymptote for this function? What is the horizontal asymptote for this function? Sam? Oh, yeah. Oh, sorry. Yeah. Okay. What is the horizontal asymptote now? What is the equation for the horizontal asymptote? Horizontal asymptote is going to be y is equal to minus a third. This is case 2. So when the terms have the same degree, the horizontal asymptote is the quotient of the lead coefficients. Case 1 and case 2, super easy. So when this is like this is the horizontal asymptote. Case 3 is a little bit harder. So what you've got in case 3 is you're going to end up with let's say we have g of x is equal to let's say we take a rational function like this one. We can approximate that now. It's going to be minus 4x to the 4 over minus 2x to the 3. We can simplify that. It's going to be 2x. So it's going to form some kind of a straight line. Now we simplified it a little bit too much. It's a little bit trickier, this one, because it's going to be 2x plus c. It's going to be a straight line. We call this a slant asymptote. We call this a slant or oblique asymptote. Yes. We're going to do that with, it depends which technique you learned last year, either polynomial division or synthetic division. Okay, so this is our third case. In the third case, the numerator has a higher power, a higher degree. And in that case, it's going to have some kind of a linear function like this one plus c. It's only going to be plus c if the difference between n and d is 1. If the difference between the two exponents is 2, you're going to get a parabolic asymptote, and then so on all the way up through the different powers. We don't go into it in that detail. It's going to be slant asymptotes at best on this course. So no.
Is that the end behavior or asymptote?
Asymptote. Well, sorry, no. Yeah, because this... yeah. So the end behavior does go towards this. The asymptote will be the division of the two. Okay, let's have a go at writing the equation of the asymptotes and giving reasons. So here for the first one. What will be the asymptote for this? Explain to the person next to you, giving your reasons. Make sure when you give your asymptote, it's in the form of an equation. All right. So, as the degree in the numerator equals the degree in the denominator, the horizontal asymptote is y equals 3/5. Okay, have a go discussing the second one. Give your reasons.
Exactly what makes it snap. Exactly what makes it a leak snap. No, it doesn't make a difference. So my extra
Me too. All right, let's have a look. Let's have a look. So as the degree in the denominator exceeds the degree in the numerator, the horizontal asymptote is y equals 0. Okay, I will start a new video for the polynomial division.